Hi, our goal is to compute the limit as x approaches 0 from the right of the function sine x divided by x and show that it is equal to 1. This is one of the more important limits in calculus, but the goal of this video is to make as few assumptions as possible and as elementary assumptions as possible. There are many videos online explaining this, how to compute this limit. However, their assumptions are often more complex. For example, like assuming that the area of the circle is equal to pi times the radius squared, which is rather complicated to derive. Here, we will use just two assumptions of Archimedes and several other assumptions that are pretty natural. Let us briefly discuss the assumptions that we're going to use. The first one is a very natural assumption that says that given any 2 points on the plane, A and B, the shortest distance between these 2 points is a straight line. Which means if I denote the length of this line by y, then any other curve that I would draw that would connect A and B would be longer. So the first axiom that I want to use can be written as y less than equal to x, where y represents the straight line segment connecting A and B, and x represents the length of any other arc connecting these 2 points. Our second assumption will have to do with convexity. Note that this region here that is bounded by the line segment AB and by the arc whose length is x is convex. What that means is that if I take any 2 points inside this region, no matter where they are, and I look at the line segment connecting them, then this line segment stays completely inside that region. If we now draw a second arc connecting the points A and B, but we draw it so that the resulting region that is bounded by the line segment AB and by this new arc still remains convex, then the assumption is that because this arc is actually outside of the arc of length x, then its length is greater than the length of x. The way we're going to use this assumption will actually not use something that looks like an arc, but rather like 2 line segments. So if I draw one line segment from the point A like this, and another line segment from the point B, and they intersect, then these 2 lengths, which I will now denote by B and C, they, together with the line segment AB, form a convex region. This region here is still convex. So the second assumption about the lengths of boundaries of convex regions still applies, and it will tell us in this situation that this line segment, or rather the 2 line segments together, are actually longer than the arc x. So this is going to be our second assumption. So let's now apply these considerations to our situation. So here on the picture, you have the unit circle, which is centered at the point O. And in this unit circle, we draw an angle BOE. And first of all, note that right here, we have the exact same situation that we just considered. We have the arc of the circle, whose length is x. We have a straight line segment connecting the points E and B. And we have the 2 line segments that are tangent to the circle, whose length are B and C. In fact, of course, B and C must be equal, but it actually doesn't matter for us. So let's just write down the inequalities that we had before that concern this situation. So the inequalities were y is less than x is less than b plus c. Now let's look at this triangle here. And this is a right triangle. And it's a right triangle whose hypotenuse is equal to y and whose one of the legs is the green line segment that I denote by A. And we clearly then have that A is less than y, as a leg of a right triangle is always less than the length of its hypotenuse. But if we now consider this triangle here, this is also a right triangle. And in fact, the angle right here has the same measure as x. And if we want to compute the sine of this angle, then we see that its sine is equal to, so sine of x is equal to a divided by 1. So in other words, what we get is that a is equal to sine x. So what I'm going to do, in order not to introduce too many variables that we won't need, I'm just going to write sine x instead of this a over here. And the same in our inequalities. Finally, let's look at this triangle over here. And this is also a right triangle. And if I write d for the length of the hypotenuse of this triangle, then we see that d as the hypotenuse is longer than the leg b. So we can write d plus c being greater than b plus c. Finally, let's look at the big triangle. And we see that this is also a right triangle. And in here, we see that we have an angle of measure x. So let's write down the tangent of this angle. The tangent of x is equal to d plus c divided by the length OB. But the length OB is just the radius of this unit circle, so is equal to 1. So we have that this is d plus c. So this last term here is actually equal to tangent x. From this sequence of inequalities, let's extract these that are important to us. And the first one is the fact that sine x is less than x. In fact, less than or equal is all we need. And the other one is that x is less than or equal than tangent x. The d plus c is equal to tangent x. Well, we can rewrite tangent x as sine x over cosine x. And dividing the first inequality by x, we get that sine x over x is less than or equal to 1. On the other hand, multiplying by cosine x and dividing by x, we get that cosine x is less than or equal than sine x over x. So from these together, we are able to squeeze sine x over x in between two expressions. One of them is equal to 1, and the other one is equal to cosine x. Now, using the squeeze theorem, we get that if we take limits, as x approaches 0 from the right, of all three terms, then the inequalities still stay valid. So we get the following. The limit of 1 is just 1, so I get this. On the other hand, as x approaches 0 from the right, cosine x approaches 1, so this limit over here is also equal to 1. So what we have done is, we know that the limit of x, as x approaches 0 from the right, of sine x over x, is actually squeezed in between two 1s. So we get our final conclusion, that limit as x approaches 0 from the right of sine x over x must be equal to 1. Why do we need to assume that the shortest path between 2 points is a straight line, and that if I have two convex regions, the arc connecting the two points on the edge of the complex region that lies outside must be longer than the one that lies inside. What if we didn't make these assumptions? Could we still prove that the limit of sine x over x is equal to 1? Well, the answer is not really. In mathematics, you have to make some assumptions in order to be able to derive other properties that you're interested in. These assumptions that you don't derive are called axioms, and you can choose different systems of axioms. Now, you may argue that the only axioms that are assumed universally in mathematics are the axioms of the Zermelo-Fraenkel set theory, together with the axiom of choice. And you would be right. So can't one derive the limit as sine x over x, as x approaches 0, using these axioms? The answer is yes. However, one loses, or at least obscures, the connection to geometry. In fact, if you look into Rudin, he derives the limit of sine x over x using a different definition of the function sine x. Namely, he defines sine x using the exponential function as e to the ix minus e to the minus ix divided by 2I. The exponential function, on the other hand, is defined via Maclaurin series as the sum from n equals 0 to infinity of x to the n divided by n factorial. From this, one can show that the derivative of e to the x is equal to itself. And now using this fact, one can compute the derivative of sine x using chain rule and see that the derivative of sine x is ie to the ix plus ie to the minus ix divided by 2I, which just gives you e to the ix plus e to the minus ix over 2, which is the definition of cosine x in analysis. Furthermore, if you compute the limit as x approaches 0 of cosine x, this is now an easy exercise. Using this definition, you see that what you get is 1 plus 1 over 2, as when x approaches 0, e to the ix goes to 1. So the limit of cosine as x approaches 0 of cosine x is equal to 1. Using this, now we can compute the limit of sine x over x by applying L'Hopital's rule, which tells us that that limit is equal to just the limit of cosine x over 1. And this limit we have computed here, it's equal to 1. So we get that the limit of sine x over x is equal to 1. However, if you use this definition, the connection to geometry is lost. There are no right triangles, no angles to speak of. Lastly, please note that you cannot apply L'Hopital's rule to compute the limit as x approaches 0 of sine x over x if we use the geometric considerations. To use L'Hopital's rule, you need to know the derivative of sine x. And if we use the geometric definition of sine x, then to compute this derivative, you actually need to know the limit of sine x over x as x approaches 0 to start with. So this would be circular reasoning.